In this lesson, we're going to talk about using the integral as an accumulator. And to start out with, we're going to jump back to finding the area between a function and the x-axis. Essentially, as we integrate this function, f of x equal 4 minus x squared, from 0 to the right, our integral is going to represent the value of the area above the x-axis minus the value of the area below the x-axis. So as we move from left to right, from 0 to 2, our integral value is going to be increasing, as we saw in the table on this Desmos example before we put in the absolute value. So let me take out that absolute value, and you will see that in our table down here, at x equals 0, if we integrate from 0 to 0, we've accumulated 0 area. If we integrate from 0 to 1, we've accumulated 3 2/3 total area. As we integrate from 0 to 2, 5 1/3. And as we integrate from 0 to 3, we start losing accumulation. So there's negative accumulation. It's dissipating, I guess, so to speak. So we can treat the integral as an accumulator of things. And I'd like to use this example to help illustrate that. So here's what we have. We have the following. We have something we're going to call big R of t, and it's kind of an ugly function. Negative 1/6 t to the 4th plus 3t cubed minus 119 over 6t squared plus 56t minus 54, and that is the rate at which water is accumulating in a container in centimeters per hour. And we are going to look at that on the interval from 2 to 6 hours, the closed interval from 2 to 6 hours. So R of t is the rate at which water is accumulating in some sort of container on the interval from 2 to 6 hours. So the question is, how much does the water rise from t equal 2 to t equals 6 hours? Well, if we think about that graphically, what we could say is we have this function R of t, and it's going to be units of centimeters per hour, and we don't know exactly what that function looks like. We'll just say it looks like that. And on the horizontal axis, we're going to have t in hours. And so if we were to look at the integral from t equal 2 to t equals 6, and we look at that area, again, go back to when we first did this with rectangles, this area here would represent, well, centimeters per hour times hours would be the total accumulation. And it would be in units of centimeters. So that's how we can treat the integral as an accumulator. So the answer to this question, how much does the water rise from t equal 2 to t equals 6 hours? Well, that answer to that question is going to be the integral from, not 2, but not 0, but 2 to 6 of R of t dt. And since we don't want to spend a whole lot of time finding that antiderivative, we're going to use fn int on our calculator, and we're going to integrate the function R of t from a lower bound of 2 to a lower bound of 6. So let's jump over to our calculator and see what we get there. So the first thing we want to do is we want to punch this function in, and we want to take our time doing this to make sure we get it correct. So there's a negative 1/6 coefficient for the t to the 4th power, or x to the 4th power, there is a 3 coefficient for the x to the third power. There is, oops, I'm going to take my time here. I want to make sure I put a plus sign in there. So I'm going to insert a plus sign. 3x cubed minus 119 divided by 6 times t squared, or x squared, plus 56x minus 54. Okay, and we're going to put that in as y1, but now we're going to jump back to the home screen and we're going to use fnint to integrate that from 2 to 6. So math number 9, 2 is our lower bound, 6 is our upper bound. The easiest way to get that function in here is to hit alpha and the trace key and select y1, and then we are integrating that with respect to x, our dummy variable in this case, even though we use t in the problem because our calculator is forcing us to use x. And we hit enter and we get 6.756 to 3 decimal places. So the answer to our question is approximately 6.756 centimeters. That is how much additional water accumulated in the bucket from t or whatever the container was, from t equal 2 to t equal 6. So we can use this idea in all kinds of various examples. The next thing I want to do is an example from our textbook, and it is related to energy consumption. In this example, the energy consumption is, or cost of consumption I should say, is represented by the function E of t is equal to 600 over 1 plus t squared. And the units, I think, are always important. And this is cents per kilowatt hour. And again, without getting into actually graphing that function, we're going to put that on the y-axis, and we have this function E of t here. And t is going to be on the horizontal axis, and that is in hours. And the question is, what is the cost in cents for 1 kilowatt of electricity use during the time period from 6 to 12 hours? So we're interested in integrating this function on the interval from 6 to 12. Again, I don't know what this curve looks like, but I do know that that area that we end up with there, and again, some of it could be below the x-axis at times, this area is going to be in units of cents per kilowatt, because cents per kilowatt hour times hours cancels the hours, and we have cents per kilowatt. So we want to know the cost of 1 kilowatt between 6 and 12. Okay, so how do we do that? Well, the integral from 6 to 12 of E of t dt is going to be our answer, sort of be our answer. It's going to give us this area that we're interested in, and that will be in cents per kilowatt. And then we're going to take that and we're going to multiply it by 1 kilowatt, because we're interested in using 1 kilowatt of electricity, and that will tell us our cost. So we're going to take this function, 600 over 1 plus t squared, over to our calculator and integrate it from 6 to 12. So go back to our function here, y1, get rid of all that. 600 divided by, make sure you put the denominator in parentheses, 1 plus x squared, close those parentheses, and then we go back to the home screen. We're going to recall what we just did. We're going to integrate this time, though, from 6, not 9, but 6 to 12. and we get 49.204 for an answer. So this integral is equal to 49.204, approximately equal to, cents per kilowatt. And we're interested in the cost of 1 kilowatt. So 49.204 cents per kilowatt times 1 kilowatt. The kilowatts cancel out, and we get 49.204 cents. And the point of doing this was to illustrate that we can use this accumulator idea in all kinds of different examples. And you will see much more of those later on and in the homework.